Okay, so can you hear me? Hello? Hello?
Yes, sir.
Yes, sir.
Okay. Okay. So there is a steel ball is there. So let me just draw it. So there is a steel ball. Okay. So diameter is 4 centimeter. Rho is 7800 kg per meter cube, and Cp is 473 joule per kg per degree Celsius. Okay, and the temperature here is T wall, let's say, is 90 degrees Celsius. Initially 90 degrees Celsius. Maybe I'll just, instead of making things complicated here, okay, I'll just write it here itself. So this is okay. This is 4 centimeter. Okay. Other than that, a row of the ball is 7800 kg per meter cube. Cp is given as 473 joule per kg per degree Celsius, and temperature initially initially the temperature is TW is 470, sorry, 90 degrees Celsius, 90 degrees Celsius. Okay. The ambient temperature here is T ambient is ambient temperature given as 25 degrees Celsius. What is been asked you, there is a air surrounding this steel ball. What is been asked is time required for temperature to drop down to 35 degrees Celsius. So what is been asked is, initially the temperature is this 90 degrees Celsius, but how much time will be required in order to decrease the temperature of this steel ball from 90 degrees Celsius to 35 degrees Celsius? That particular time is being asked in this case. Clearly, this is the clear-cut case of this natural convection, because there is no turbulence in the air, only the air is present outside, and the heat is being transferred from this steel ball to the ambient. Okay. So in this case, whenever we are looking at the natural convection, we need to find out the properties at average temperature. But what average temperature? Remember, the average temperature in this case has to be the average temperature between wall temperature and the ambient temperature, isn't it? So wall temperature is 90 degrees Celsius, ambient temperature is 25 degrees Celsius, but that is initially. But as time passes through, my average temperature is also going to change, because my wall temperature is going to decrease, isn't it? So my wall temperature is going to drop down to 35 degrees Celsius at the end. So in this case, the average temperature should be, average temperature is used at both the extremes. So average temperature is calculated here as 90 plus 25 by 2, that is one end. The another end is 35 plus 25 divided by 2, that is the another end, and the average of these two is used as a average temperature in this case. So that comes around 44 degrees Celsius. Did you get it, what I'm trying to say here? In general, the average temperature has to be calculated as a wall temperature and the ambient temperature, correct? In case of a natural convection. But in this case, the wall temperature itself is changing with time. So we have considered both the extremes, initially what wall temperature we had and what is the final wall temperature. And the average temperature at initial condition we have calculated, and the average temperature at the final condition we have calculated. And again further we have taken the average between that. So that is the average temperature, not only with respect to the time, not with respect to the temperature, but also with respect to the time here. Okay. Is it okay? Is it all right? So now, once we know the average temperature at the 44 degrees Celsius, all the properties are already been given in the problem itself. So these are the properties at 44 degrees Celsius. So we can use the properties of the air at this average temperature, and we can solve this particular problem. Is it all right? So now, in this case, the first thing is we have to calculate is the in this case, the first thing we have to calculate is the Rayleigh number in terms of diameter. So that Rayleigh number is given as G beta delta T D cube by nu and alpha. So this is what the formula of Rayleigh number with respect to diameter. So here we can calculate the Rayleigh number. So G we already know, that is 9.8. Beta is nothing but 1 by temperature, isn't it? So 1 by temperature, and that has to be absolute temperature. So that becomes 1 upon 44 plus 273. So that is going to be beta. Delta T in this case is going to be T minus 25, because see, Rayleigh number, when we are calculating, Rayleigh number will depend on delta T, and this delta T itself is going to change, isn't it? At both the extremes we know, but at any time in between we don't know what is the temperature of this wall. So let us assume that the temperature of the wall at any time instant in between is just a T. Okay, so that I can write down as T minus 25, isn't it? And D cube, so D in this case is 4 centimeter is given. So diameter is 4 centimeter, so that becomes 0.04 cube and divided by kinematic viscosity and the diffusivity. So let us look at what is been given in the problem. So in the problem, kinematic viscosity is given, but thermal diffusivity is not given. So thermal diffusivity is directly calculate here. So thermal diffusivity is Cp mu by K, isn't it? Sorry, that is mu by rho Cp. So that you can calculate based on the Prandtl number itself. So that becomes, if you rearrange this equation, I can just rearrange this equation. So this equation in terms of Prandtl number, we can write something like this: Td cube by nu square into Prandtl number. Okay, so Prandtl number is Cp by K, alpha, which is a thermal diffusivity, which is given as mu by rho Cp. So if you rearrange that term, basically what you are going to get is Rayleigh number in terms of diameter. You can write down this equation directly. So now the kinematic viscosity is already given, that is 1.75 into 10 raised to power minus 5 square into Prandtl number. In this case comes out to be Prandtl number is given, that is 0.695. So calculate the Rayleigh number in terms of t minus 25. Calculate the Rayleigh number. Anybody? Hello?
Yes, sir, we are doing.
So just note down here that this alpha I have replaced in terms of Prandtl number and nu. That's it. That we can do it, isn't it?
Sir, is it coming out to be 4490 into t minus 25?
Something around this I got it. Check whether this is correct or not. Is it correct?
Yes, sir. Yes, sir.
Yes,
Okay.
sir, it's 4490.
4490. 4490. Okay, I'll just make it. It doesn't matter, but I got this value, but I'll change it. Is that what you? Sorry. Is that what you are trying to say? 4.44. Okay.
4.9.
4.449. 4.49.
Yes, sir.
Sorry. So that means I have written it correctly. 4.48 and 49. That's no problem. It's perfectly all right. Okay. Okay, so now based on this, now we have to calculate the Nusselt number. So one of the correlation which we have to use here is in this case the correlation for the spherical case, which is given as Nusselt number is given as this is the same correlation which is given in the book. So HD by K 2 plus 0.589 Rayleigh number 1 by 4 divided by 1 plus 0.0469 divided by Prandtl number, this bracket raised to the power 9 by 16, and this entire bracket is 4 by 9. So this is the same correlation. If I am not wrong somewhere, I can go back and just check. Let me just open forced natural convection, isn't it? So this correlation is correct.
Sir, it's valid only for Rayleigh number, Prandtl number less than 0, greater than 0.7, and
Greater than equal to 0.7 or something. In this case, here the Prandtl number is 0.695 or something, isn't it? That is very close to 0.7.
All right, sir.
So this is the correlation. Just let me go back.
Sir,
Okay.
it is 0.469, I guess.
Just wait. I am opening that. This is the correlation. 0.469, isn't it? 0.469, correct. What I have written, 0.0469 I have written. Yes.
Yes, sir.
I'm sorry. I'll just correct it. Okay. So this is what the correlation is, isn't it? This is valid for a Rayleigh number which is, you know, greater than 10 raised to power 11, and the Prandtl number should be greater than equals to 0.7. So in this case, air is used which has the Prandtl number around 0.695. So that is very close to 0.7. So we can still you know, go ahead with this and use this correlation. There is no problem. Okay. All right. Is it all right? So I am projecting the whiteboard. Okay, so this is what the correlation is. So now in this particular correlation, we can put all the you know, Rayleigh number in this case, and we can, you know, simplify and find out Nusselt number in terms of t minus 25, because t we don't know, 8, isn't it? So just put all the values here. So this becomes 2 plus 0.589 in the bracket 4.48 into 10 raised to power 3 t minus 25 and this is raised to the power 1 by 4 divided by 1 plus 0.469 divided by 0.6959 by 16. Entire thing is 4 by 9. So calculate this value. Calculate this value. So what I have got is this. Just check whether this is correct or not. I could have made the mistake here. Just check whether this is correct.
So we get 3.711.
Sir, I got 3.709.
Correct. That is perfectly all right. No problem. It's not the problem. 3.7 you are getting, isn't it? 0, 1, 9, it's okay. Perfectly all right. That depending on how accurately you have used your, you know, other values.
Yes, sir, this is correct.
Okay. So now this is the Nusselt number. So Nusselt number in this is a Nusselt number in terms of diameter. So that is given as hd by k. So h into d is 0.04 divided by k. So k is 0.0276. That is what is been given, isn't it? So we can find out h from this, isn't it? So h comes out to be. So this is going to give me h. So h is 1.38 plus 2.558 t minus 25 raised to the power 1 by 4. Is it correct?
Yes, sir.
So this is what our h is. Now, you know, we can make a balance. So in this case, balance is, remember, whatever is the heat lost by the sphere, that should be the heat, you know, transferred by a natural convection to the ambient, isn't it? So we can write down a unsteady state heat balance. So unsteady state heat balance in this case can be written as minus m CPS dt by dt, isn't it? So this left hand side is nothing but the heat lost by the sphere, and that should be equals to the heat transfer to the ambient. So that is given as HA T minus TA, isn't it? HA T minus TA. Now mass of the sphere we don't know, that we can calculate because diameter of the sphere we know, and the density of the sphere we know. So mass of the sphere we can calculate, isn't it? So mass of the sphere we can directly write here as So we can write this as pi by 6 d cube, so that becomes 0.04 cube. So this is going to be the volume multiplied by density. So density is given as 7800 multiplied by Cp. Cp is given as 473. Correct. Cp is given as 473 dt by dt, and H we have already calculated, that is 1.38 plus 2.558 in the bracket t minus 25 raised to the power 1 by 4. This is H. Area in this case is going to be the area of the sphere. So area of the sphere again will be given as pi r square, so that becomes 0.04 square, isn't it, into t minus 25. Correct? Is it correct? Hello?
Yes, sir.
So now in this particular equation, if we rearrange all the term, we should get the expression in terms of dt by dt, and that we have to integrate. Okay. So find out the expression dt by dt. So expression in terms of dt by dt. Let us say minus dt by dt. What is the expression we are expected to get? So pi will get cancelled out. This will also get cancelled out. Becomes 0.04 divided by 6 into 7800 into 473, and that we have to take inverse. So this is going to be 4.0657 into 10 raised to power minus 5 in the bracket 1.38 plus 2.2558 p minus 25 1 by 4 into t minus 25. Again, if we rearrange the term, what we are going to get? Is it correct?
Yes, sir. Yes, sir.
So now we can rearrange the term. So basically what we can do is we can integrate this as dt divided by all these terms, so that becomes 1.38 plus 2.2558 t minus 25 raised to the power 1 by 4, this bracket close, and then there is another bracket which is t minus 25. So this is one end, and right hand side is going to become 4.0657 into 10 raised to power minus 5, and this is integration. If we take it on the right hand side, integration of dt, so that becomes t, that becomes just t, isn't it? Correct? And this limit goes from t equals to 90 to 35, isn't it? So find out the value of t. Can you solve this integral on a calculator? I don't have an answer for this. Can you do it?
Yes, sir. Let's calculate.
I think around 6484 seconds is expected. Just check whether that is correct or not. I'm not sure. 6484 seconds.
Yes, sir. It's coming up to be 6488 seconds.
So 6484, that is what I got it. So around this you should get the value. Is it all right?
Sir, could you just wait for a second?
Yes. We have time. No problem. One more problem we will take from tutorial number 8. So how many classes we are left with in general?
Sir, I think we're on lecture 15 or 16.
15 lectures are remaining.
No, sir, we are on lecture 15 or 16. Correct.
But okay, so that means around 6 or 7 are left, isn't it?
Yes, sir.
Yes, sir. The answer is coming very close.
Okay, perfectly all right. So this is going to be the time required for dropping the temperature from 90 degrees Celsius to 35 degrees Celsius. So but here you can see the time required is much higher. If you look at the real life example, this time could be lower than whatever the time we have obtained here. The reason for that is in a real life situation there will be a turbulence in the air, isn't it? Some turbulence in the air, so it is not purely a natural convection. Okay, so the time will be in actual condition, the time will be lower than this. Okay, so now let us look at the second example from tutorial number 8. Okay, let me copy this example in a tutorial sheet here, and then we will go ahead. Okay. So anyway, these equations are not coming here. So can you look at the equations in the tutorial sheet? The equations are not coming in when I am copying the things. Okay.
Yes, sir.
So please let me check if I can download the equations here. No equations. I'm unable to copy the equations here. So just bear with me. You can look at the equations directly in the tutorial sheet. Is it all right? Hello, is it all right? What we have to prove here is, maybe I can write it down. Yes, I'm sorry, I just forgot
Yes,
that I
sir, we
can
can
write
see.
it. Okay, so what we have to prove here is H. Okay, what we have to prove here is H is given as KL divided by R ln R delta minus ln R. So this is what we have to prove in the first case, and the second proof is 1 by 2 plus R delta divided by R square ln R delta divided by R minus 1 by 2 equals to 2 KL rho L LV, latent rate of vaporization, TW minus TB, R square and T. Okay. So these are the two expressions which we have to prove here. What is been given in this problem is the condensation of a saturated vapor occurs on the outside surface, outside of a tube under zero gravity. So this word zero gravity is very important. Okay. A condensate film will form on the surface but will not run off because there is no gravity. So that means the film will keep on forming around the surface outside the tube, but it will not fall down. Okay. Now in such cases what we have to prove is if a pseudo steady state approximation is done, uh, the heat transfer coefficient is given by uh, H is given by KL divided by R ln R delta minus ln R. So that we have to prove, and then finally what we have to prove is this expression in terms of R and R delta. We have to find out how the time is related to this. Okay. So now what is been given here, let us look at things in a little bit in more detail. Let me just scroll it up a little bit. Okay. So what is been given is, let us assume that there is a tube. There is a tube. So there is a tube like this. Okay. Now outside of this tube, outside of the tube, because of condensation, the film okay, because of condensation the film is formed outside this tube. So this is a tube. Again the radius of the tube is, let's say the radius of the tube is R, and radius of the outer layer is R delta, and the length of the tube which is shown in a Z direction, where here Z direction is perpendicular to the plane of the screen. So along that direction the length is L, isn't it? Length is L. Okay, that is what has been given. Zero gravity means what? Zero gravity means whatever the film of the condensate is getting formed around the tube, that is not falling down. That is what the zero gravity is going to be in this case. Now in this case rate of heat transfer is given as rate of heat transfer. So rate of heat transfer is given as Q, in this case is given as, remember this is a cylindrical system, isn't it? So for a cylindrical system the rate of heat transfer by conduction can be written as, directly I am writing this expression. So TV minus TW L divided by ln R delta by R. So this is the same expression which we have seen in the conduction from the cylindrical system, isn't it, earlier? So I am writing down this equation directly. There is nothing new in this. Okay. Now rate of condensation, let us find out rate of condensation. So rate of condensation. So rate of condensation in this case can be written as directly. So change in the mass, isn't it? So change in the mass of this system here can be directly obtained as density rho L into pi square L. So that is going to be the change of the mass. So that is nothing but, see, change of the mass is primarily coming from what? It is coming from the condensation itself, isn't it? So d by dt rho L pi r square r delta square L, that is going to be the change. And so this differentiation, if we do the differentiation, what we are going to get is rho L pi as it is into L. This will remain as it is. R delta into 2 into dr delta by dt. This is what we are going to get, correct? Now this rate of condensation, remember this rate of condensation is primarily because of what? This is primarily because of the heat transfer, isn't it? So we can equate that. This can be given as, rate of condensation multiplied by latent heat of vaporization. So that is going to give me the amount of heat transfer. So that becomes LV is nothing but the latent heat of vaporization multiplied by 2 pi rho L R delta dr delta by dt. So this is going to be the amount of, there is a L is also there, isn't it? So L, and this should be equals to the amount of heat transfer. Okay. So 2 pi KL TV minus TW L divided by ln R delta by R. Remember, there is some word is being used in the problem statement, pseudo steady state. So why we are calling it as a steady state? So this is primarily, remember this, the amount of heat transfer is calculated at a state, isn't it? This is a steady state expression. But if you look at the left hand side here, that is varying with respect to temperature. So that is why in the problem statement it is given that at a pseudo steady state condition. Okay.
Sir, can you please repeat that?
Okay, which one you are saying?
So the pseudo steady state.
Okay, so here if you look at this expression of the Q, this expression of the Q is at what? This is the rate of heat transfer at steady state, isn't it? Correct. This is coming from the Fourier's law of heat conduction. So here we are assuming that the steady state is already been achieved. Correct. Right. But if you look at in this particular balance, if you look at the left hand side, there is a change. This, if you look at the radius here, this R delta is changing with time, so it's not steady state, and this balance is being made. That is why in the problem statement it is mentioned clearly that you make a pseudo steady state balance, so that pseudo steady state approximation has to be used. So that is what it means. Is it all right?
Yes, sir. Sir, I also wanted to ask, while you were taking dm by dt, so shouldn't it be the difference of the two squares, the radius?
You are saying that difference between these two, isn't it? That is what you are trying to say?
So while you calculated rate of condensation, you were calculating dm by dt.
I understood. What you are trying to say is
Yes.
this is nothing but the density multiplied by the we are basically doing the volume in this case, isn't it?
Yes, sir.
So you are saying that since we should consider only the volume of the outside the film, isn't it? That is what you are trying to say?
Yes, sir.
Okay, just wait. I think some in the problem statement something is given along that direction also. Just wait. Okay. No, see here what we are looking at is if you look at this rate of condensation means how much amount of condensate we are adding. What how much is the differential amount of condensation we are adding in the system that we are calculating, correct, isn't it? So this pi r square is basically giving me what that is giving me the outer surface area, isn't it? That is giving me the outer surface area into L. So that is giving me the volume of this entire thing. But you are right. You are saying that we have to take the difference between this pi r square r delta square minus r square. That is what you are trying to say.
Yes, sir.
Okay.
Sir, I guess the final expression will still remain the same because r is a constant, so derivation में वो
So
zero is.
derivation is going to become zero. Yes, yes, yes. But we have to put it correct way. Let me just. Okay. Okay, but after differentiation we get still the same thing. Okay, all right.
Yes, sir.
Okay, so after this this is the balance equation where we are assuming that the rate of condensation multiplied by latent heat of vaporization, so that becomes the total amount of heat being transferred during the condensation, and that should be equals to the amount of heat being conducted through the film, isn't it? So that is what is equated here. So we can rearrange this particular equation. So what we get is, I'll just scroll it up a little bit. So if we rearrange this equation, this 2 pi will get cancelled out. So finally, the simplified form is this r delta ln r delta minus ln r dr delta kl tv minus tw. This lv I have taken on the right hand side into rho l dt. This is just the rearranging the terms here and there. So this ln r delta minus r, that becomes ln r delta minus ln r. This is the bracket which is taken from the right hand side, multiplied by this r delta as it is, and into dr delta, isn't it? That is going to be on the left hand side. This 2 pi will get cancelled out. This rho l is coming on the left hand side here in the denominator. This L will get cancelled out with this L. And this LV is also taken on the right hand side here. So on the right hand side, these are the additional term plus KL TV minus TW into DT. Okay, is it all right? Now we can integrate this equation. So integrating the above equation. So after integrating, what we are expected to get is, remember this is going to be integrated by using integration by parts. So what we are expected to get is, I am writing down the expression here, ln r delta square by 2. This is the first term, minus 1 by r delta. So that is the differentiation of this, into r delta square by 2 into d r delta. This is this equation coming out from the integration by parts, and the last term is remaining here. So this last term is going to be ln r is constant, so that remain as it is, del and this r delta multiplied by ln r delta. So this r delta is there, so that becomes r delta square by 2. So this is going to be the integration of the left hand side, whereas the integration of the right hand side, we are going to get it KL TV minus TW LV by rho L dt. And if we further rearrange things, what we get is ln r delta square by 2. This is the first term. This second term, the integration of the second terms comes out to be r delta square by 4, and the third term obtained is ln r into r delta square by 2, and this is equals to KL TV minus TW LV rho L T plus C. Okay, is it all right? Now, in this particular equation, the boundary condition we can put it as, at t equals to 0, r delta should be equals to r. Okay, at t equals to 0, r delta equals to r. That what it means is, at time t equals to 0, initial time, there is no film around the horizontal tube, and therefore r delta is just equals to r. So if you put it in this particular equation, what we get is the constant of integration c is obtained as, constant of integration c comes out to be minus r square by 4. Is it okay? Is it all right?
Yes.
So these two terms are going to get, this first term is going to get cancelled out with this term. So only this last term is, and this becomes 0. So c becomes r square by 4, minus r square by 4. That is what you are going to get directly. Now you can put it in the original equation. So let's say this is the equation number, let's say 1. You can put it in equation number 1. So what you are going to get is, from this, what you are going to get is r delta square ln r delta by r by 2 minus r delta square minus r square. So this is c is taken out on the left hand side, is taken on the left hand side, so that becomes this particular bracket, and the right hand side we left with only KL TV minus TW LV rho L into T. So what we have done here is, if I go back, So this C is R square by 4. I have taken it here. Okay, so this ln R delta, so R delta square by 2 I have taken common here. So that becomes R delta square by 2 ln R delta minus ln R. So that becomes just ln R delta by R. And this R square by 4 is there. So 1 by 4 I have taken common here, and that becomes R delta square minus R square. So this is what the final expression we are going to get it. So this is, let's say, equation number 2. So if you rearrange this equation further, you can rearrange, you can multiply these two to the entire equation. So this 2 goes here. Okay, and you can divide by R square. So this becomes R delta square by R square. This becomes KLTV minus TWLV rho L R square, and this becomes R delta by R whole square minus 1, isn't it? So if you divide this entire equation by R square, and if you multiply this entire equation by 2, so maybe I just write multiply equation 2 by 2 by R square. Okay, if you do this, what you are going to get is directly I am writing down R delta by R. This is the whole square in the bracket ln R delta by R minus 1 by 2 R delta square by R square minus 1, and the right hand side is going to become 2KLTV minus TW divided by rho R square T R square T. And if you further rearrange whole square, we have taken common. So this becomes ln R delta by R minus 1 by 2. This 1 by 2 term is remaining here, so that becomes plus 1 by 2 equals to 2KL TV minus TW rho L R square T. So this is what the final expression which is being asked in the problem statement. This is the second part of the proof. Okay. Now in the first part we have to calculate the heat transfer coefficient, isn't it? In the first part we have to calculate the heat transfer coefficient. So heat transfer coefficient here is obtained as heat transfer coefficient in this case is obtained as what? H is given as Q divided by 2 pi RL, that is the area, into TW minus TV minus TW, sorry, TV minus TW. Okay. So remember, heat transfer here, Q is given as what? H into 2 pi RL TV minus TW, but Q you can also write in terms of conduction, isn't it? So this is given as, in terms of conduction, Q can be written as 2 pi KL TV minus TW into L divided by ln R delta by R, and this is divided by this entire denominator, which is nothing but 2 pi RL TV minus TW. So all the common terms get cancelled out here. What you get here is H is obtained as KL divided by R ln R delta by R. So this is the first expression which we have to prove. Okay. Is it all right?
Yes, sir.
Okay, these are the both the expressions for the given condition. So we stop here unless there are some questions. So is there any questions from anybody?
Yes, sir, I had a question. Sir,
Okay.
the previous tutorial, when we were finding the cross-section area for
Okay, I will project that. I'm sorry, I just forgot to project that. I'll project that. Just wait.
All
Okay.
right.
So that is, I think, for one batch, some problem was there, but other batch, second batch, Tuesday batch, we have done it correctly. Just let me save this and then I will project, export image. Okay. Okay, so in the last tutorial for the Monday batch, what mistake we have done here is, remember what is been given is when we have calculated the cross sectional area. So cross sectional area when we have calculated, so I will just go to the cross sectional area, then you will understand what I'm trying to say. Okay, so cross sectional area when we have calculated, remember we have said 10 transverse rows present, isn't it? That when we said in the problem statement itself that there are 10 transverse rows are present, that is what said in the problem. But for your Monday batch, what we have done is here 5 into 0.025, that is what we have done the mistake for Monday batch. Okay, but if you look at the tutorial answers, this whiteboard file which I have uploaded, and also I told you that follow the video which is downloaded on Tuesday batch. So that has done it correctly. So this is from the Tuesday batch. So here instead of 10 we have used the 5 in a Monday batch. So that is what the mistake we have done. Okay, why it should be 10 and why it should not be 5, that I will come to very soon. Just wait. So what was the mistake in our understanding was in the problem what is been given is, if you look at, there are 10 transverse rows. So when we are counting the transverse rows, this is the transverse pitch. Remember, this is the transverse pitch. When we are counting the transverse rows, this 1, 2, 3, these 3 are coming in one row. This is not the second row. This is not the second row. Remember, the transverse pitch is between this and this. That is what has been given. So cross-sectional, see, the only difference in Monday batch and the Tuesday batch was, in Monday batch we have assumed only 5 such transverse tubes here, and there are additionally, see how many total number of tubes are there. Total number of tubes are
120.
120, isn't it? So if you are using 5 here, so additionally the columns are going to increase, isn't it?
Yes, sir.
But that was the mistake because the transverse pitch is between this and this. It's not between this and this. So this is not counted as a transverse row. This is not counted as a transverse row. Transverse row is this.
So then we'll have 240 tubes then.
Why 240?
Because sir,
Why?
it says that there are 10 transverse rows.
So this anyway is counted in the column. See, this is column as one row, isn't it? This is counted as one row. So 1, 2, 3. This in this manner we will have almost 12 tubes present in one row and 10 along the vertical direction. Okay.
So
So maybe I'll just give. I will explain. Okay. So see. What is the difference between staggered and the aligned one? In aligned one, this is just at the top here. This is at the top. You get it?
yes, sir, the bottles are all in the same row.
Yes. This is instead of having it in between here, in a aligned case, this is just goes up here, up. Okay. So there we count this in a one row itself. In a staggered also these are counted in a one row because these equations are derived in such a manner. Okay.
Oh.
Okay. So
So
this is not a separate row. This is not a separate row. The first row is this entire thing from this is going in a zigzag manner. That is the first row.
all right, sir.
So that is one point which I wanted to clarify. The another point which I wanted to clarify is you can argue that then when we are having the 10 tube here, then it is just 9 into the 9 should be counted instead of 10, isn't it? Because the cross sectional area is this, isn't it? That is what you are trying to say. But some space is left here and some space is left here, and that becomes one more, length for the one more tube there. Okay. So in it is basically counted as a 10 instead of 9. That is another justification. That is why we have multiplied 10 into, if you look at 10 into the area is calculated here. So 10 into 0.025 into 1. Perfectly all right. This is the transverse pitch. 0.025 is the transverse pitch. All right.
Sir, shouldn't it be 9
That is
9
what I'm
times
saying.
plus 2 diameter?
That is what I'm saying. 9 you are saying because it's the upper portion you are not counted and the bottom portion you are not counted, isn't it? I am saying there will be some space available at the top and some space available at the bottom. It is not directly starting from the center of one tube to the center of the last tube. Did you get
Yes,
it?
sir. Sir, shouldn't it be matlab exactly equal to d, the extra space?
It should be exactly equal to.
Diameter, because radius will be left
It's not
at the top.
radius. Here, it's a transverse pitch which is being used. See, I'm just coming. See, when we are looking at the cross-sectional area for the flow, I am not looking at this tube. I am looking at how much area is there from this point to this point here. That's it. What happens in between here, that effect, since these tubes are in between and therefore the velocity is going to increase, that effect is accounted in Vmax. That is why we are using a Vmax here. That is why we are using a Vmax here. That effect is accounted here. Did you get it? That is why we are not using a V here in all the calculation. Even the Reynolds number is calculated in terms of Vmax. Is it clear?
Yes.
Yes, sir.
Okay. Any other doubt or?
Yes, sir. Sir, I've emailed it to you. Can you please share screen?
Let me just check. Okay. So these corrections we have done, correctly in a Tuesday batch in the last tutorial. So please follow the Tuesday batch, the video as well as the actually I have uploaded the correct one in a MS Team, but video you have to take the Tuesday batch video. Okay. So what is the correction? What is the doubt here, Vishruta? I'll just share yours.
So can you scroll down?
Just wait. Can you hear me?
Yes, sir.
Okay, so let me just scroll down. Okay, what is the doubt?
Yes, sir. Here. So we
It's the
did
end
not.
of the file.
Yes, sir. That's it. So we did not include the mu 5e term.
Where?
So where in this energy equation for convection.
Okay, just let me just open this. So this is the free convection you are saying, isn't it? Natural convection, isn't it? This is the natural convection thing.
Yes, sir.
Okay, let me just share that file. Then probably I will be able to understand what is the doubt. Okay. So this is what you are asking?
Yes, sir.
Hello?
Yes, sir.
So where is the doubt?
In the energy equation for convection.
In the energy equation for convection, yes.
Yes, sir. So we did not include the mu 5e term, which is supposed to be there for the heat transfer.
Mu 5e, what is this term you are saying?
Sir, it is related to the viscosity, the viscous dissipation. So we did it last year in transport phenomena.
Yes. You are saying that uh, the increase in temperature by viscous dissipation we have not included. That is what you are trying to say?
Yes, sir.
Yes. I agree with you. We have not included that term. Yes. So that becomes important here. It is not that important in this case. But if you look at the flow through the extruder or channel where the polymer is flowing, in such cases viscous dissipation is also increase in temperature, and there that term has to be included. I completely agree with you. Yes.
And sir, in the equation 3, so can you please explain where this continuity equation came from?
So see here, basically the continuity equation is the okay. So here, what is continuity equation? Whatever is coming in, the same thing is going out. Okay, that is what the continuity equation is, isn't it? Correct. So this is not derived. This is just written. What I am trying to say is, when you are trying to solve this entire model equation, this also will be another equation which you have to include while solving.
So, but what's the logic behind it?
What the logic behind it is, in this case, what we are assuming that at a steady state, if the amount of material is going in, the same amount has to go out. That is what the continuity is.
So, but this
Isn't
is
it?
just the like gradient of velocity in x direction.
So this equation you can directly get it from the mass balance if you apply. This is the standard equation equation, if you go back and look at your transport phenomena, this is the standard equation which derived in the first class, isn't it?
Oh, all right.
So this is in addition to this energy balance and the momentum transfer. This will also be a binding, kind of a constant. This should not be violated. Okay, that is what it means. So even continuity equation has to be satisfied.
Okay, sir.
So for example, see, when we are looking at the a standard fluid mechanics problem, if you look at the restricted channel, if you look at suddenly the diameter of the pipe is decreased, in that case you apply the continuity equation to calculate what will be the velocity, isn't it?
Yes, sir.
So amount remains same. Only thing is that since you are now decreasing the diameter of the pipe suddenly, in a same amount your velocity is going to increase. So this is the same thing. This is the same thing that the which is coming in, the same amount will go out, and that is what is called as a continuity equation in a simple term. Is it all right?
Yes, sir, got it.
Okay.
And so while in the previous tute itself, so while we were writing the expression for Nusselt number, so we used the expression PR by PRW.
Yes, PR by PRW. So that basically accounts the viscosity. So for example, if your viscosity changing too much at the wall because of increase in the temperature, in that case PR by PRW, this factor is PR number Cp mu by K, isn't it? So
Yes.
PR by PRW in a way is mu by mu W. That is in a way is a ratio of viscosities, wall viscosity and the bulk viscosity.
So can we change, like, are they interchangeable?
So if you see, in this case, we are assuming that the only viscosity is changing, but a Prandtl number also has another two parameters, Cp mu by K. Isn't it? Cp can also be varying. Thermal conductivity can also be varying. If suppose if you are working with a fluid where with temperature, even thermal conductivity is varying. In such case, the more accurate expression is PR by PRW, isn't it? And if the activity and the specific heat is not varying, in that case only mu by mu W will work out. So that is what is used in Cedar-Tate equation, if you remember, isn't it?
Yes, sir, that was also in one of the equation, mu by mu W.
Correct. So mu by mu W is a simplified version of PR by PRW. Actually, it should be PR by PRW. In most of the cases, viscosity varies with temperature compared to the specific heat and thermal conductivity. So thermal conductivity and specific heat is in general is considered constant, nearly the constant, and therefore mu by mu W is used instead of PR by PRW. All right.
All right, sir.
Okay. Any more questions?
No, sir, that's it.
Sir, the temperature difference here in natural convection is in y direction, so density will vary in y, but why the fluid motion is taking place in x direction?
What you are saying?
Density difference is in y direction, but the fluid is moving in x, y.
Just natural what you are saying is density difference, okay, but why the density difference is in a y direction, but why the motion in the x direction is considered? That is what the question is.
Yes, sir.
Okay, just wait. Let me share the file. Is it already shared? Okay, this is what you are saying in this particular slide. You are saying